This video is about nozzle effect. Nozzle is a conic module added at the end of the water hose to give excess speed when the water is coming out. From the momentum perspective, it is a very interesting module. Let's learn it from the scratch. I modeled the nozzle as a cone or maybe a tube with two different cross-sectional areas. Here I have a cross-sectional area of A1 input and the cross-sectional area of A2 on the output, or let's say left side. The water speed in input is U and the water speed in output is V. They must be different. The reason? Because we believe that the total mass in and the total mass out in the nozzle must be equal at the same time. We believe in conservation of mass. The nozzle cannot generate water inside or disappear that. So the total mass in, total mass out are equal always. Based on that, the total volume, the volume in and the total volume out at the same time are again equal because density of the water is constant. So if the masses are equal, volumes also are equal. Let's say we have a cross-sectional area of A1, as I mentioned, and the distance traveled by the water at the time of delta T is H1. Here A2, and the distance traveled by the same mass of the water is H2. So the volume in is base times height, A1, H1, a cylinder. The other, again, base of the cylinder, A2, in the output, times H2. As A2 is smaller than A1, so we can say H2 is larger than H1. Let's divide them by delta T. H2 over delta T must be, again, larger than H1 over delta T. So H2 over delta T is going to be V, which is larger than H1 over delta T, which is U. Now I proved that the output speed is larger than the input speed. But why we consider this system in momentum perspective? Let's make a system including the mass of the nozzle and the mass of the water in, which is traveling at the time of delta T inside the hose. Okay? This system has a conserved momentum because there is no external force acting on that. Now we see that the nozzle, the capital M, is giving an extra momentum to this mass of the water, leftward. So it will have a reaction on the nozzle, rightward. This is why the nozzle is pushed back, just because it gives an excess momentum to the water. Why? The momentum in is the mass of the water times U, the input speed. Here we have the same mass but different speed. So the momentum out seems to be M times V. The momentum out is larger than the momentum in. So there is a change in momentum. Change in momentum of the water and the change in momentum of the hose must be equal. They should cancel each other according to conservation of momentum. So the action that the tube, the nozzle, gives to the water will result in reaction on that. And so that reaction will push the hose back. It's very interesting, and it's called the nozzle effect. So let's consider the nozzle from the scratch again and find equations. Here I have F, which is delta P over delta T. Delta P over delta T is change in momentum, rate of change of momentum of the water at the time of delta T inside the hose. And this force is the force generated due to this change of momentum. And at the same time, we can consider this force as a force exerted on the water or the reaction of that on the hose. So be careful that this force is also sensed by the nozzle, rightward. So you should hold the nozzle because of this excess force to cancel that. Otherwise, it will go for a chaotic behavior and will dance to all directions. Okay, now let's continue. Here, mass can be substituted for density times volume. Okay, let's consider the output cross-sectional area. They are the same because mass in and mass out are equal. So can we consider the output cross-sectional area? So volume could be like this. Let's say the water travels for delta x at the time of delta t. So instead of volume, we have cross-sectional area times the distance traveled. Okay, let's do it. This volume is A times delta x, and this density is density of the water. Delta V over delta T is U minus V, is larger, minus smaller. V minus U divided by delta T. V minus U is a change of speed inside the hose due to the different cross-sectional areas. So this is the delta x, the total distance traveled by the water inside the hose in the output cross-sectional area. So I substituted everything as mentioned. Then we can rearrange the equation and take the delta x here to make a fraction delta x over delta t. Look at the output here. The delta x over delta t is exactly something which is called the v, the output speed. So we keep rho a, v minus u times v, the output speed. This is the force, action or reaction force due to change of speed inside the hose. If the hose has the same cross-sectional areas, actually is not going to be a nozzle anymore, just a hose, a tube. Here the speed in and the speed out are equal, so there is no v minus u and there is no nozzle effect. This is why the nozzle can absolutely create a very interesting effect due to the change in the momentum of the water inside. Anyway, let's consider a limitation. Let's say the input cross-sectional area is much larger than the output. So it's expected that we have a negligible u relative to v. So u is very small, so we can approximately ignore it. Instead of v minus u, we can ignore the u and write it as only v. So estimate equation could be rho a v square. This is just applicable in the cases that, as I mentioned, the input and output cross-sectional areas are dramatically different. Otherwise, the original equation is this one. Now let's consider a question. A mass of 0.48 kilogram of water leaves the garden hose every second. So here we have delta m over delta t, rate of change of mass, to be 0.48 kilogram in every second, kilogram per second. The nozzle has a cross-sectional area of this. This is the output cross-sectional area. Be careful because the input cross-sectional area is the cross-sectional area of the hose. It's nothing that important. This is the cross-sectional area mentioned for the nozzle, the output. 8.4 10 to negative 5 in SI units. The water flows at the hose speed of the input speed in the hose to be 0.71. So the U is given to be 0.71 meter per second. Density of the water also given. Calculate the output speed, the speed at which the water leaves the hose. So we are looking for V, the output speed. How to find it? It's very easy. We can use this delta M over delta T because we know everything except the V. Let's start it like this. Delta M over delta T is 0.48. For delta M, we write density times the volume. The volume, the output, as the distance traveled is considered to be delta X, is going to be cross-sectional area of A times delta X, A times delta X. So it's A times delta X. Now we rearrange the equation and make a fraction like delta X over delta T in output. This is exactly the V. We are looking for V. Okay, we have everything except V. Let's do it. The rate of change of mass is here, density of water here, 8.4 10 to negative 5, the cross-sectional area, and the V is obtained as 5.71 meter per second, the output speed. The part B of the question, the force produced by the nozzle, is exactly the nozzle effect. As I mentioned, this force is going to be rho A, V minus U change in the speed in the nozzle times V. Okay, the output speed. Let's plug in the values. Density of the water here, the cross-sectional area of the output, V minus U. V is something that we have already imported from the previous part A. 0.7 is given here, and I've rounded it to be 0.7 instead of 0.71. 5.7 again, the same output speed. So the answer is going to be 2.4 Newton. The force, the action or reaction force generated due to the change of momentum of the water inside the hose. That's it. Thank you very much. Thank you for watching this video. If you find it useful, share it with others. See you.